Okay, so before we go straight to the axioms and axioms of addition and multiplication, let's quickly revise what natural, integer, rational, real, and complex numbers are. As one of my videos, natural numbers are those numbers that are counting, just like natural numbers are also called counting numbers. So that is apart from zero. So we have 1, 2, 3, 4, 5, 6, 7, 9, 10, down to positive infinity. Now, for integers, integers are positive and negative whole numbers, including zero. So natural numbers are positive whole numbers, excluding zero. Now, for my rational numbers are, the name sounds, ratio. So it means what? I have numbers such as 2 over 4, 1 over 3, minus 1 over 5, minus 7 over 15, minus 300 over 4,000, and so on, or 4,556. Now, and then I have complex numbers. Complex numbers as a form, that is z equals a plus ib, or x plus iy, or r equals to x plus iy, in which case it can be defined. So now, after knowing all those, it means that we can now go straight to our axioms of addition and axioms of multiplication very quickly. Now, when you hear axioms, axioms basically means law, the laws guiding the addition and then the multiplication rules. So we have we have C, and then for multiplication we have C, I, A, I have G, I have M, and I have C. Now, how do we mean? These are the abbreviations for the axioms of addition. It makes me to easily remember them while solving questions. So C here represents closure, the closure property. The same thing here, the closure property. Then I represents, for this, that's the identity. Okay, let me label all this first. So then I have this as additive inverse. Additive inverse. For this I have the associative property. Associative property, and then for this I have commutative. Okay, so for multiplication, I mean, this is also my identity. For this I have it as associative property or associativity. For this I have it as distributive property or distributivity. For this I have it as my multiplicative inverse. For this I have it as my what? Commutative or commutativity. So as simple as that. Now, these are the axioms. Now, how do we now define these axioms with elements of what? Of my real numbers, as an example. Now, for you to define it, you need to define some real numbers under real numbers. How do I mean? So I can say from the start, I can say let A, B, and C be coming from what? Set of real numbers. That is, A, B, and C can represent any element, any number. Okay, so I forgot to define real numbers earlier. Real numbers basically are a set of numbers that includes your rational and integers. That is, the ones involving your fractions and the ones involving your positive and negative whole numbers. So this also positive and negative fraction. Now, so let A, B, and C be what? Coming from what? Set of real numbers. It implies that for closure property, A, let me use plus in this case. This is plus, right? So A plus B is equals to C, element of what? Real numbers. What do we mean? If A is 1, B is 2, 1 plus 2 is equals to 3, right? It means 1, 2, and 3 must come from what? Set of real numbers, which is actually very true. Because 1, 2, 3 are what? Are real numbers. Okay. So more specifically, they are what? They are integers. Okay, so let's continue. For identity, we have for positive that's for addition, axiom for addition, we have our identity to be represented as E, which is equals to 0. That's the first thing. My identity is E, which is equals to 0. which means that A plus E is equals to what? A. Okay, which is equals to what? E plus what? A, element of what? Set of what? Real numbers. That is, if my E is 0 automatically in axioms of addition, and my A is say 2, 2 plus 0 must be equals to 2, and 0 plus 2 must be equals to what? 2. Very simple. For additive inverse, if A, B, and C has been defined already under set of real numbers earlier, for additive inverse, I can say A plus B equals to B plus A. Now, when my B equals to what? When my B equals to minus A. Now, how do we mean? For A inverse, additive inverse of A, it means changing the sign, of that particular element. So if A is my base element, it means that what? A plus B here is what? Minus A. A plus minus A must be equals to what? Minus A plus what? Plus A, which is equals to what? Identity. It must be equals to my identity. All element of what? Set of real numbers. That is, if my A is 4, that becomes what? 4 plus what? Minus 4. That's what? 0. 0 is what? Is E. If my A was also minus 3, this becomes what? Minus 3 plus minus 3 plus minus 3, because this is minus A. So that becomes minus 3 plus 3, which is equals to what? 0. And then that is the idea there. For this associativity, if A and B has been defined and C has been defined, it means A plus B or plus C must be equals to what? A plus what? B plus C. That is, no matter how I arrange it, all are the same thing. So if this is 1, 2, 3, that becomes 1 plus 2 plus 3. So this is 3 first, then plus 3, that's 6. This is 1 plus 2 plus 3 is 5. 5 plus 1 is what? 6. They must all be what? Elements of what? My set of real numbers. And for my commutativity, just picking 2. So A plus B equals to B plus A, element of a set of real numbers. That is, no matter how I arrange it, 2 plus 3 must be equals to what? 3 plus 2, which is equals to what? 5. That's for addition. So that's that about axioms of addition. Now, straight to axioms of multiplication. What do we have? For closure property, just like we had for addition. Now for multiplication, A and B and C being defined as elements of set of real numbers, it implies that I'm going to have this as what? A times B must be equals to what? C. Everything must be equals to what? Or everything must come from my set of what? Real numbers. So if I have 2 times 3, 2 times 3, which is equals to 6, must all come from what? Set of real numbers. That is, 2 is an element of real number, 3 is an element of my set of real numbers, and 6 also is an element of my set of what? Real numbers, which is very true. Now, for identity, just as we had for addition, for multiplication, E is always equals to what? Always equals to 1, anywhere, anytime. Now, in this case, identity now becomes what? A times E must be equals to what? E times A, which is equals to what? A. Now for addition, remember we said A plus E equals A equals E plus A. This is the same thing as saying A times E, equals E times A equals to A. All come from what? Set of what? Real numbers. That is, if I have 4 times 1, it must be equals to 1 times 4, which is equals to what? 4. As simple as that. Now for associativity, in this case, if I have A times B, all times C must be equals to what? A times what? B times C. That is, if I have 1 times 2, all times 3, that becomes 9. This is the same thing as saying 2 times 3, which is what? 1 times 2 here is 2. 2 times 3 is 6, I mean. Then we have the same thing as what? 2 times 3 is 6. 6 times 1 is what? 6. Now, all must come from what? My set of what? Real numbers. Now, for distributivity, now it's such that if I have A into B plus C, that is A times B plus C, it must be equals to AB plus what? AC. Now, if I also have A plus B all times C, it must be equals to what? AC plus what? BC. And all this must come from my set of what? Real numbers. That is, this times this plus this times this, as simple as that. So, for multiplicative inverse is when I have A times B equals to B times A, all equals to E, where my b now in this case is equals to 1 over what? A. Now this is just like reciprocal. Now what's the reciprocal of a? That's 1 over a. What's multiplicative inverse of a? That's 1 over a. So that is, if I have something like say 4 times now inverse of 4 will be what? 1 over 4. That becomes what? 1 over 4 times 4. All must give me what? 1, because they'll cancel themselves out. As simple as that. And they must all come from set of what? Real numbers. Finally, commutativity. Now for commutativity is when I have a times b to be equals to what? B times a, vice versa. So element of set of what? Real numbers. That is 4 times 5 must be equals to what? 5 times 4. As simple as that.